So what are AI agents? What are large language models? What is a chat model? All of these things are things that I hear all the time, and I also hear people getting confused about and mixed up about all the time. My name is Shay Brown. I'm a PhD in astrophysics. I was a professor of astrophysics for 11 years. I then founded and still run an AI auditing, assurance, and testing and evaluation company, Babel AI. And I run a community for continuous learners and people who are trying to struggle with the concept of learning in the age of AI where everything is at your fingertips. And I hear this a lot. These sort of concepts get mixed up, and there's a lot of confusion around this. And so today I wanted to take a little deep dive into this and try to break apart some of these concepts and see if we can get some clarity around this. All right, so let me first start with sort of the most basic and simple sort of building block of all this. And I'm going to make use of a Colab notebook that I created for some training and just some explanation for myself even on how these things work. And so at a really basic level, so forget the word transformer decoder for a second. At a really basic level, large language models are attempting to do exactly what they sound like, model language. And so in order to do this, they take a natural language like the kind you see here, where you see both implementations have been simplified by only having a single decoder block with a single self-attention head, right? This is a sentence in natural language. And in order to do anything, the computer is first going to have to take these words and turn them into numbers. And that process is called tokenization. And so if you scroll down here into this little block, there's a prompt, and we'll forget a prompt for a second. Let's focus on the sort of this gray box here, which is the sort of the fundamental, the underlying model. And so you're going to take sentences or words, and you're going to tokenize them. You're going to give them a number, basically. And there's a mapping between words and numbers. Now, sometimes it's partial words because you want to be able to compose things and make words that are more complicated than you might have in your dictionary. But in either case, it's going to map numbers to words. And then it's going to take those individual numbers and it's going to turn them into a whole list of numbers. So each number, each token is going to be turned into a vector. And so I'm not going to go into this. I've talked about this in other places, but I have a word, and that word is going to be turned into like a long list of numbers here. We call it a vector, but it's got a number here, a number here, a number here, a number here. And this vector, if you've ever taken physics, you can think about it a little bit like an arrow. So here's some coordinate space, but this arrow is going to represent a particular word. And the reason we do this is because we'd like to have the representation of those words mean something relative to each other. And so a nice example is if I have the word cat here, then this little arrow, which is another embedding, another list of numbers, might be kitty, right? And they are close to each other in this space, which means they kind of are used in similar contexts and they are similar in some way. Whereas, dog might be over here and puppy might be over here. And the thing that is interesting is the relationship between cat and kitty ends up being the same relationship that dog and puppy have. And so these embeddings allow us to capture some sort of meaning. But let's not dwell on that for a second. It's just a bunch of numbers, right? And so these numbers get crunched through a bunch of matrix multiplications. And for the most part, we call this a transformer. And there are different kinds of transformers, and I don't really want to worry about the different kinds that we have here. Just know that you take sentences and that have words which you represent as tokens, and you embed them, and you multiply those numbers by a bunch of other numbers. And the process at the end, what comes out at the end of this, if you train it on a lot of data, is basically the next token. And so I'm sure you've heard people say that these models, all they're doing is predicting the next word. And you might be kind of confused because you type into ChatGPT and you see it's producing all sorts of words and all of that. So what's actually happening? Well, what they do is that this gray area here is that very base model. And what it's doing is it's going to feed in a bunch of words. This will happen in the training process. So maybe it's fed in this sentence. And what it's trying to do is predict the next word after been is simplified in this context. Now, of course, if you feed in all sorts of language from the internet, it's going to see this word many, many times. It may not see all of this context many, many times, but still, all it's trying to do in the training process is predict what's the most likely next word after this sort of set of words. So that is done in a fairly straightforward way. It's called semi-supervised learning, but they just keep feeding all of the language of the internet and books and everything else that's been written, and it gets very good at predicting the next word. And so, okay, that's good, but how is that the same? How does ChatGPT use that? So once you have a model like this, then you can start to do what's called auto-regression. And so what you can do is you are going to predict the next token. And so now you don't actually just predict a single token. What comes out of it actually is a whole distribution of potential tokens. So what am I plotting here? Along the x-axis, or along this sort of horizontal axis, is possible tokens. All the possible tokens that you could have, right? So every word, fragment of a word, they're all in a big long list. So this is has the length of your entire dictionary with all words and all possible words and all languages. And what this line is representing is the probability that what comes after the thing you just put in, the prompt, what's the probability of this particular word being the next word? And some have a very low probability and some will have higher probabilities. And so the way these auto-regressive models work is, now that you have this machine that can predict the next token or predict this distribution, you need to somehow select which token do you want to generate after that. And there's different techniques for doing it, and I won't get into it, but you can pick the highest one, or you can randomly select from the top 3 or the top 5. There's all sorts of different methods. But this selection of the next token, this is where the randomness comes in. And so people often talk about these systems being quote unquote stochastic or random. That's kind of true. So for most of this gray box, this probability distribution is actually not random, meaning if I feed in the same text, I'm going to get the same probability distribution out. So for the same prompt, I'm always going to get this probability distribution once the model has been trained. But I have to make a decision, me, the programmer, how am I going to select the next token? Because I don't always want to pick the top probability one. Sometimes maybe I want a little bit of randomness in there. And so this method of selecting the next token is where the randomness comes in. And it's governed by this thing called temperature. And if you set the temperature equal to 0, it ends up not being random. It becomes deterministic again. You always get the highest probability. Okay, so I have this method now for selecting the next token. And what I'm going to do is something very simple. I'm just going to add that to the next prompt. So I'm going to take this prompt, the original one, add that next token, and now I have a new prompt. And I simply feed it back in. And so this is the auto-regressive, I'd say transformer decoder, because this is what the original GPT models were. This is a way of generating text. So I give it a prompt, which might be this sentence here, and then it's going to start spitting out one after another new tokens or new words. And that's what you see in the chat response. Now, it obviously stops. So how do you know when it stops? How does this system know when it stops? Well, the way it knows is that there's a special token, which is the sort of end of the response token. So if I were training this and all I was feeding it was this one sentence, then I would put a little end token here. And so after the period, which would be the last token, I would try to predict the end of this sentence or the end of this input. And so within all of the tokens and that probability distribution that gets spit out like this, there is a slot for stop, basically. And so when it eventually comes to what would be a natural end to the response, it is going to have the highest value probability be that stop token. And then it says, okay, I'm done. And the system stops and the autoregression stops. Okay. So this is the base of everything that we see now with these large language models. They have this sort of gray block, which is the input-output thing, which says I stick a bunch of text in, and what I come out with is just a probability distribution for the next token. So I know what's the most likely token, I know what the second most likely token is. And for the generative AI aspect of it, to generate new things, I have to have a method for selecting the next token. So that's where that randomness comes in. And once I have that method, then I just append it to the prompt and feed it back in, and it just goes around and around and around until it gets to a stop. So that's the basic idea, or the basic underlying structure of these whole systems. Now, there are all sorts of details here which I have skipped. And in fact, I can link this notebook if people are interested. There's all sorts of details, and you can see that it's sort of spelled out here, some of those details. And there's not just details in the architecture. And when I say architecture, I'm talking about how are these little blocks of numbers stacked together. There's also details in the training process, how these systems are trained. And that could often includes a sort of a first step where I'm going to do, sometimes they call it pre-training, but I have my little block, which is my large language model. This is my block. And I put text in and I get text out. And normally I put text in and I actually get the next token out. And so the next token. And all I do is I take every piece of writing in the world and I stick that text into there. I chunk it up in different ways. And I teach this little black box, this transformer, to predict accurately the next token for all of the writing in the world. So this is sort of like the pre-training phase. And so once you're done with this, you have a nice large language model that is able to kind of model the language. And so meaning it's able to infer what the next token would be. But it's not that great at answering your responses or doing other things. And so what they do then is sort of supervised fine-tuning. That's it doesn't always have to work like this, but this is a pretty common recipe. And so for the supervised fine-tuning, what they do is they take a bunch of different or more data, which is structured in a very particular way. If you want to have a chat model, you're going to structure it in a way that I'm going to ask a question, and then I'm going to get a response. And so I take a lot of these, and this is where a lot of the sort of manual labor has come in. You have to generate lots and lots of these questions and lots of these responses. And then you're going to do the same thing that you did before. You're going to take this text in and predict the next token. But when you do this, oftentimes you'll kind of like freeze some of you don't want it to forget too much. So you'll freeze some of the weights. The weights are just the numbers that make this inference. And so you're gonna sort of hold some of this fixed, and you're just gonna change it a little bit based on this supervised fine tuning. You're gonna get it to be better at acting like a nice, helpful assistant. And then there are different stages where there's also reinforcement learning with human feedback. And do I want to get into reinforcement learning and human feedback? Why not? So what is that? Okay, so reinforcement learning with human feedback is, how do I make this even better? So now I've pre-trained on all the text in the world. It's really good at predicting the next token. Now I've taken a bunch of sort of specialized data to make that thing much more like a helpful assistant. And so it's going to respond in ways that I like. And you can do some sort of alignment here where I want it to be nice and various other things. I don't want to spew out toxic language and things like that. That can happen here. And then what I'm going to do is I'm going to try to make it even better. So you remember that sort of random aspect I talked about? Well, what if I take some text, and what I do is, instead of just producing one response, I'm going to reproduce several responses, making use of this sort of randomness aspect where it starts generating different responses. And then what I'm going to do is I'm going to get a person, or many, many people, to look at these and tell me which responses are better. So you might have seen this even when you're interacting with some models. They'll ask you a question. They'll give you multiple responses and they say, which one do you think is better? And this is a way of sort of labeling and ranking these things. So this is the human feedback part of the reinforcement learning with human feedback, is you get humans to kind of rank this. Then that's not enough because there are only so many humans in the world. What you're going to do is you're going to have another model over here. So this is a box. So I like boxes for models because black box. So here's this model, which is the original large language model. Oftentimes you can just make a copy of it, or you can use a totally different model, but you have another model and you're going to use all of this data from the human feedback and you're going to train a reward model. So this is a model which is, the inside of it is very much like a large language model. Well, why? Because it has to understand language in order to understand what's going on. So it is a large language model itself, but you've restricted it in a way to only output, given a set of responses, a prompt and a set of responses, which response is better. And so you teach this thing to rank responses. And so you use human feedback, and now once you have enough of this, you have this new model which can, for multiple responses, tell you which one a human would think is better. So it's encoding the human feedback. So once that happens, once you have this model, then you can get rid of human, and which is the ideal thing for these sorts of, to scale these sorts of things. So now I have this model, and I'm going to take the large language model, keep feeding it more text, more questions, let's say, and I get more responses. And now my model is doing the ranking, not the human. My model, which is sort of has been tuned and trained to be like a human, and then I can just run this in a loop. So as long as I have a bunch of questions, even if I don't have the answers or prompts, I can still rank the outputs using this reward model. And as you do this, you can change the model. So you can change the weights of the model using reinforcement learning. Don't worry about reinforcement learning. All it is just you have a reward, and you use that reward basically to adjust the model so that it gets better at giving you things which are going to get a higher reward. So that's all reinforcement learning is. And to be honest, it looks very similar to this kind of mathematics over here. It's not super different. So I have this reward model, and I'm going to, once trained, now I can just let it keep running. Now, of course, the limitations are the reward model is only as good as the humans and the input data that it was trained on, and so this can only go so far. But nonetheless, it sort of tends to be the final step. There might be some, you can always do more, but then this gives you, GPT 3.5 or something like that. This is where a lot of these models came in. So this is the basic idea, and this has been sort of the state of the art a couple years ago, not even a couple, maybe a couple of years ago, or even a year and a half ago. So now the question is, what actually happens with when I'm interacting with the model itself? And so sometimes when you're typing in, you will see it searching the web, or you will see you're able to upload a document and actually have that document somehow incorporated into the responses. And so I'm going to stop for now, and next time I think I'm going to talk about what's the difference between what I just showed you here and those cases where it's searching the web, it's scanning through documents, and then eventually we're going to talk about this weird agents and this agentic behavior that everybody's talking about.